So welcome to the Flip module where we're actually going to use OpenCV and video analgesic together to come up with some interesting image processing operations and really get access to the wealth of functions and the open source community that contributes to OpenCV. So let's get started. So the agenda that we're going to look at today is we're going to look at using OpenCV in the iOS environment. Now, we're going to be using this as a tool, as an API. We're not going to get too much into all of the nitty-gritty that's part of OpenCV, although we will talk about some of the basics. What we're really going to focus on is more of the outputs of each algorithm, how to use the different methods, how to use the different semantics and functions that are built into OpenCV. But for the most part, we're really going to ignore what's under the hood, what's going on in the C++ code, right? We're just going to use it as an API. So OpenCV is a giant computer vision library. It was originally built by Intel and it was open sourced by Intel, but since then it has had a family of active developers that have worked on OpenCV, and it's really become an industry standard for working on computer vision problems. It's very fast. It works across many different operating systems. It works with many different languages. There's actually quite a few wrappers for OpenCV, so you'll see it used in Python, you'll see it used in the .NET framework through usually the MGU or VC++. There are Java APIs that are built for it, so you can also use it with Android, and many, many more implementations. Now, it doesn't have a wrapper yet specifically for Swift at this time of the filming. However, we're still going to be able to use Swift, and I'll show you how in just a moment. Now, one thing to keep in mind is that when we were using core image, if we set it up properly and we set up the context for which the images we're using, we were always running on the GPU, right? However, OpenCV does not know the hardware that it's running on. It is not necessarily running hardware accelerated on the GPU, especially in iOS. However, the wrappers that people have built around iOS take advantage of the Accelerate framework. Now, this is the same Accelerate framework that we actually use for a lot of the audio processing that we had. But inside of this Accelerate framework, it's going to be used for image processing. Now, that means that it's probably slightly slower than using the GPU, but it's still very, very fast. It has that parallelized multi-instruction architecture. So when we want to go through OpenCV installation, there are a few different methods that you'll need to do. Now, you won't have to go through all of these explicitly, but if you wanted to download OpenCV and install it from source, you would need to do it through downloading the OpenCV framework for iOS. Now, you can go onto OpenCV's website and actually do that. And they have Python code that you can use to actually build it from scratch. Now, that may or may not work depending on the libraries that you have installed, the different dependencies that you have there. There's also an OpenCV implementation you can use CocoaPods for. So there's many different ways that you can get the very latest version of OpenCV. Once you have that built, it's going to create what's called OpenCV2.framework. And this is just like any other framework in iOS. So Core Audio is a framework, AV Foundation, UIKit, these are all frameworks that when we used explicitly Objective-C, we actually had to drag them or add them to the project explicitly. Since we've been using Swift, a lot of those frameworks are already, if we use a core image framework, it knows that it needs to import it. In this implementation, we'll have to drag, there's an OpenCV2 bundle.framework that we actually have to drag into the project. Then you may have to manually add quite a few dependencies depending on how your system is set up. With the new Swift framework, a lot of the manually adding of dependencies like AV Foundation and Core Image, you have to explicitly tell the compiler that you're using those. But with the new Swift implementation, a lot of that is taken care of for you, so you may just have to drag in the OpenCV2 framework into your project and use it. You can get step-by-step instructions at the link that you see here, and also in any of the iOS tutorials for OpenCV. There's a lot of people that use this, and so that means there's a lot of resources at your disposal for using and installing OpenCV. One thing you'll have to note is OpenCV is written in C++. Now that means that you will have to use C++ code in whatever model or view controller that you have OpenCV being used. So you'll have to rename those from the .h and .m files to .mm files, and that way the compiler knows that it expects C++ code inside of there. Alternatively, if you just want to use a default installation, I'm actually going to give you access to a Xcode project called Image Lab. We've been using it actually in class. I've updated that, and you will see branches now that have OpenCV installed. You can actually just do a checkout of the branches where OpenCV is being used, and all of this is taken care of for you. OpenCV has been dragged in, the dependencies that need to be there are there, and you can just use it straight out of the box. So before, what we've been doing is using video analgesic. However, there are many different ways of getting access to images from the camera if you want to use OpenCV. There are many online tutorials that will show you how to set up a video camera module. You'll use something called a CV video camera, and you can actually set yourself up as a delegate to use the CV video camera protocol. However, this tends to be a little bit slow. There are a lot of clunky implementations on top of OpenCV for getting access to the camera in iOS. So I've actually built a wrapper for video analgesic, so you can use the core image framework and the OpenCV framework right side by side, just using the video analgesic functions that we've already been using. And it's as simple as using something like this. The first thing that we're going to do is declare our OpenCV bridge variable. Now, what this is it's a link to code that has been written in Objective-C and C++. So by calling and getting an instance to the OpenCV bridge, that is how we're going to be able to transfer images from core image to OpenCV and from OpenCV back to core image. And if we can do those conversions, that means that we can use video analgesic right out of the box. So if we want to do that, inside of our processing code, once we have this OpenCV bridge, all we have to do is call self.bridge.setImage, and we'll actually give it an image that it needs to process. We can say with bounds, so we can actually give it a rectangle. Let's say we could right here, what I'm actually giving is this is the input image to set image. With bounds, I'm actually giving it the entire bounds of the image. So process the whole thing, all of the pixels. But I could have actually given this some different bounds that I had right here as a core graphics rectangle, a CG rect. I can actually give it whatever I want it to process, and it will only process inside those bounds using OpenCV. That can be really good when you want to accelerate by just processing OpenCV on a smaller number of pixels or smaller image. And then the context will always have to give it the CI context that we're working on. Okay? Then I'm going to call the function self.bridge.processImage, right? So what that actually does is now that I've set the image, it will do all the OpenCV processing that I need it to do. This is, if you don't call this, it will never process that image, right? So calling self.bridge.processImage, that's what you do when you want to run the code that you've written, whatever that code is inside of the OpenCV bridge class. The next thing we'll do is we don't have to do this, but if we want to get the actual processed image back so that maybe we can display it, we can call self.bridge.getImage, right? And that will return a core image. It converts it from OpenCV after the processing is done into a core image, and that means we can return that inside of the video analgesic function and actually display anything that we want to coming back from OpenCV. So it's a very powerful way of using core image and OpenCV right side by side with one another. Right? So there's a couple of different ways to use the set image and get image function. And so specifically the get image, I'm going to show you one more way that we could use it. Right? So let's say that we're actually using a face detector. So let f right here equal get faces. And let's say that that returns to us all of the CI face detected images that we have. Well, one of the things that we could do is when we call set image, the bounds that we could give it is maybe we only want to process the face. So I give it the bounds where the face has actually occurred, the first face that it detects. And so now the image that it sets in here, it's only going to be using OpenCV to process the bounds around the face. And everything else is the same here. And then you'll also notice I'm actually getting a slightly different function. Instead of using the get image, I'm going to say get image composite. Now, compositing is a process of taking one image and somehow putting it and combining it with a background image, right? So anything that you've done in Photoshop would be compositing. You do a lot of compositing of images and you combine things together. What this compositing does is it actually takes the OpenCV image and the bounds that we had, so we're only processing this, and it actually places it back into the original image that we gave it, but it replaces the pixels, right? So we can actually see a live view of the entire image and where OpenCV has processed part of that image. And the only part that you'll see that has been composited is the OpenCV processed image. The rest of it will be exactly like we gave it, right? Now, that OpenCV bridge function that we had, all of that is written in C++. And what you're going to do when you want to process an image is you're actually going to head over to the opencvbridge.mm, right? So this is Objective-C and C++ code put together. And inside of there, there's a function called processImage. That is a function where you can process any of the images that you want using C++ code and using OpenCV, right? So inside of this processImage function, underscore image is whatever that input image is that we set, except it's now an OpenCV matrix, right? So it's an OpenCV map. So matrices are how OpenCV deals with all of the images. It's very much like, if you're familiar with Python or MATLAB, it's like a matrix or a NumPy implementation of how it saves all the images. So what I'm going to do is I'm going to call a couple of OpenCV functions right here. And you don't have to know exactly what these are. It's pretty intuitive, but essentially what we're going to do here is I'm going to convert the color of my image to a grayscale image, right? So the way that OpenCV works here is here's the input image and the destination image, right? So I'm actually going to save a converted color going from blue, green, and red to just a grayscale image. And that'll be the source and destination. And then I'm actually going to do a bitwise not, right? So what I'll do is I'll do a bitwise not on the input image and save it into the underscore image. Now, you don't have to know exactly what this code is doing, but essentially one thing you have to understand is underscore image is your input image. And however you manipulate that, whatever you save into underscore image, that is what will be called and displayed to the screen if you were to call the getImage or getImageComposite from this OpenCV bridge class, right? So whatever you want to be displayed, make sure that you save it into the underscore image at the very end of the function, right? Now, you can do anything inside of processImage that you want to as long as it's valid C++ code. So if I wanted to do some thresholding, I could convert the color of image, right? So I go from color, BGR, to gray, so this makes it grayscale. And then I can actually threshold this using a binary threshold and something called Atsu's method. So it's just kind of a method of, let me look at the histogram and find a place that's a really good place to threshold this image. And then I can take that image copy and save it into the underscore image that I have right here and convert it back to the BGRA format that it was in. Add it back to the display. So there's a lot going on in here, a lot of syntax for OpenCV. So let's actually look at this for a moment. Inside of this processImage function, you are not on the main queue. So if you try to do any UI updates, you're not going to be able to do it from the processImage unless you actually call dispatch async get main queue. Another thing is, if you're using this out of the box, I want you to know that this is not the latest version of OpenCV 2. Or actually OpenCV. I'm using an implementation slightly older. I think it's 2.10 of OpenCV, right? So it's not the latest version. However, if you want to use the latest version, you can absolutely download the very newest OpenCV 3.0, download it onto your machine, build it from source, and just drag over that framework if you wanted to. You can absolutely do that if there are some functions in OpenCV 3 or 3.0 that you want to use that are maybe not built into this older version of OpenCV. Most of the things that we'll do, the simple filtering, the simple processing, are going to be part of the OpenCV package, the framework that's already inside of the Git repository. Now, this version of OpenCV and even the newest version of OpenCV are mostly updated in terms of the iOS wrapper that's being used. There are a couple of things that they use that are deprecated, but they currently work. They're not throwing errors. And it also means some of the transformations that are used for, say, transforming back to a view are not quite up to date. Those are all just things that are part of the wrapper, not OpenCV in general. So those are things to keep in mind when using inside of this processImage function. One thing to remember is you are not on the main queue inside of processImage. So let's actually do an OpenCV setup demo and see how we can use part of this Git repository of the code that I've already written for you. So here we are in the main screen using Xcode here with our image lab with our Image Lab project. Now, what we're going to do here is, what I've already done is inside of image DSP utils, I've already dragged in a few things. The first one is the video analgesic.swift, which we've been using and we've used before. The second is our OpenCV bridge files, so our .h and .mm files. Now, the second that I tried to pull those over into my project, so it immediately asked me whether I'd like to take these OpenCV bridge.h and .mm and put them in the, put a bridging header together. Now, what that actually does is it exposes different classes that are written in Objective-C to our Swift code. So if I actually look at this, the only thing that it does is import OpenCV bridge.h. And all that means is that anything that's in this public API right here will also be available in my Swift code. So all of my Swift code will have access to my OpenCV bridge functions, right? So if I look at the .h file for OpenCV bridge, we can see quite a few functions that we've actually already gone over. Now these are written in Objective-C, but immediately we can already see our set image, we can see our two get image functions, and then also the process image. We'll talk about these other functions later on. So what I'm going to show you here is inside of our viewController.swift, when we actually wanted to use this, I'm going to say let bridge equal OpenCV bridge, and it's that simple. It calls the initializer. This is like calling alloc init for an Objective-C function, for an Objective-C class that we have, right? So bridge now is completely set up as an OpenCV bridge class instance, and that means I can call things on it, right? So if we go over here to well, let me show you here. We have our video manager, which is of type video analgesic. We get the shared instance, and I immediately set it to use the front camera, right, the FaceTime camera. And we also are actually still doing some face detection inside of this code, just like we had done in class before. So I'm going to set the processing block, and I'm going to tell it to use self.processImage in the Swift code, right? So the process image function that I have right here, remember this is our Swift code, so this is inside of video analgesic. It's not the OpenCV process image. I'll show you that in just a moment. What I'm going to see here is all I'm doing is detecting faces, right? If I don't detect a face, I immediately return the input image. So I will never even call any OpenCV functions. If I don't see a face, I'm not going to use anything. I'm not going to actually run any OpenCV code. Otherwise, I'm going to define this return image variable, and then I'm actually going to call self.bridge.setImage, and I'm going to give it the input core image that we're getting from the camera. I'm going to use bounds the entire image, do processing on the entire image, and I'm going to give it the context. Then I'm going to process it and get the image back, get the entire image back, right? So what it'll actually do here is whatever is written inside of our process image function inside of OpenCV bridge. Right, so I can actually go over here to the OpenCV bridge.mm and see what's happening inside of this process image function. Now, there's actually a lot going inside this process image function, but the only thing I'm going to show you for this first demo is exactly the first thing we talked about here. The only code that's getting called is convert color and do a bitwise not. So I convert it to grayscale, and then I do a bitwise not, which is basically the white pixels become black pixels, the black pixels become white pixels, and the grayscale pixels turn into the inverse of those grayscale pixels, right? So it's just doing a bitwise not on the image. Anything that was dark before becomes light, and vice versa, right? So I'm going to run this on one of the phone that I have right here. I'll actually see what this looks like. So it turns out that we're actually going to deprecate the get image, and we're just going to use get image composite from here on out. So we'll use get image composite right now. So I will run this. Let's see what we can actually do here. Okay, so it is running. Now my face is kind of there, but you can't actually see it yet. Now the second that I put my face into view, we'll actually transfer this image over for OpenCV processing. So there, right when it detects the face, immediately we've done OpenCV processing. So if we go back, come over, go back, come over, and it's as easy as that. Okay, so now let's move beyond the OpenCV setup demonstration. So before we get too far, I want to bring up some convenience methods that are part of the video manager, the video analgesic function. And the first one is actually going to be the toggle flash button. So if you call self.videomanager.toggle flash, you will actually turn the flash on the backside on or off. Right? Similarly, there's a toggle camera position where you can actually tell it to go from the front to the back camera or the back to the front camera and vice versa. If you're using a iPhone 5S or better, you can actually set the flash level, right? And so you'll actually do that with self.videomanager.turnOnFlash with level, and then you give it a value between 0 and 1, which controls the brightness of the flash. And so here I'm actually coming from a UI slider. So whenever the value is greater than 0, I attempt to turn it on with a certain level between 0 and 1. And then if the value is 0, I'll simply call turn off flash. Right? There's also a turn on flash button in addition to the toggle flash button. So there's quite a few convenience methods for you to be able to use. So you should go ahead and look at the public API for video analgesic and get an idea of what some of those convenience methods are. Okay, back to OpenCV. So there's a number of various operations that you can do. And you've already seen we've done some color conversion, the convert color function. One thing to keep in mind is all of the input is saved as a matrix, a CV mat, right? It's very similar to NumPy, very similar to MATLAB. Everything is stored in terms of rows and columns. Now, if you're using a format where you have a sensor with blue, green, and red, that means you would have 3 different matrices. One that has all the blue sensor values, another that has the green sensor values, and another with the red sensor values. However, by default, when we've actually captured from the camera that's part of iOS, it's actually a BGRA format. So there's an alpha channel, an alpha format that's built into there. So there's actually 4 different matrices. So if we want to convert anything over from the alpha value to something else, we need to convert from BGRA to whatever color format we actually want to go to. Now, another thing to point out, because these are matrices of data, it's actually stored as just contiguous stack memory, right? So a matrix is just a huge array of all of the values that are inside that, inside the format. And so I'm going to show you some code here, but if we want to get access to the pointer to that array, the very first pointer, the very first element, we can actually call CVMat right here. So image is a type CVMat. I can call .pointer, and I can give it the row and the column for which I want a pointer to inside of the array. It's a very fast operation. So it starts from the upper left, and it actually goes BGRA. So that's the way that the matrix is set up. So it knows that what the stride is of each of those pixels. So if I say the row and column for, say, 1, 5, it knows to skip all of the BGRAs until I get to the 5th pixel in the first row. So this is actually the image pointer I can use for accessing pixels and also setting the pixels. So in this example, let's say that I have a BGR format. That means when I go for int I equals 0 to 50, so basically on a diagonal from 0 to 50, I'm going to set each of those pixels. I'm going to set the blue pixel equal to 255. The green and red pixels are all going to be 0. So what that's going to do is completely set a diagonal from I equaling 0 to 50, a diagonal, 50 pixels equal to blue. Okay? And it's a very fast operation using the image.pointer. Okay? Now, I can also access things. This is just a pointer, right? I can actually just access image pointer at the II, and then set point at the 0, 1, and 2 equal to 255, 0, and 0. And that's maybe a little bit faster operation. But since it is just a pointer, I can access the pixel that's actually right next to it, right? So if this is in BGR format, this is completely valid operation right here where I set the first pixel and then I set the second pixel, 3, 4, and 5, right? So there is no checking, or this is C++. There's no checking for bounds or if I've gone on beyond the image. I'm simply setting things in an array, right? And I can do this. It's completely valid code, right? So that's pixel at II. this is the next pixel in the row. So it's the pixel at I plus 1, right? The next pixel, it's the next column, the same row, right? Or if I'm at the very end of the image, it would go all the way to the next row and the very first column. So let's go over a couple of very common OpenCV operations. So the first one is filtering. Now filtering is something that we've done in core image before, but you can also very easily do it in OpenCV. It's also very fast, just not GPU accelerated. In this example, I'm actually using a Gaussian kernel where I have a 25 by 25 pixel kernel with a Gaussian with a standard deviation of 3. So the bigger I make the standard deviation, the more blurring I'm actually going to have. I can filter my image with this Gaussian kernel using filter 2D, and I have my source, my destination, and the kernel that I'm using. Or I could actually use a Gaussian blur kernel right here. So this takes care of actually setting my Gaussian kernel that I have right here. And I can actually have a little bit more control over the standard deviation in the vertical and the horizontal directions. So in this example, I am giving the source and destination, so I'm doing an in-place operation, and I'm using a 3x3 Gaussian kernel with a standard deviation of 2 in the horizontal direction and a standard deviation of 2 in the vertical direction. So, and this is a very fast, this is Gaussian blur right here is a faster operation than doing this right here because it actually takes advantage of the symmetry of the kernel that I have. We've already seen the bitwise not operation. That's simply inverting the pixels. So from 0 to 255, just flopping it, or flip-flopping it from 255 to 0. We can also take some common statistics. So if I define this scalar called the average pixel intensity, I can actually take the mean of each of the channels that I have in my image copy. So image copy here, if it's blue, green, and red, then value at the 0 right here is part of the scalar. So average pixel intensity dot val at the 0. This will be the average blue, the average green, and the average red inside of my image, right? And there's also many different color conversions that I can do. We will talk more about those later, but essentially most of the things that we're going to be doing start with either BGRA or BGR, right? So the first thing that I'm always going to want to do is convert color BGRA to BGR, and then I have access to many more color conversions. We'll talk about some of those later. But for right now, let's show some of those basic operations using OpenCV from Xcode. Okay, so what we'll do here is let's actually go over here. I'm going to source control, and I'm going to switch to a different branch. I'm going to switch to a branch where I have a couple of things already set up. Let's do a commit here. We'll do a video commit. And then we're actually going to go into source control. I'm going to load up something with many OpenCV examples in it. And it is right here in OpenCV examples, and I'll switch to that. It's also going to change some of the root view controller functionality. Now, you'll notice this one right here, we're actually calling set image and get image composite right here, which we also did on the last one. But with this one, we're only going to be doing processing on the face that's inside of the image, right? So I have this f0.bounds right here. So if there's a face, I'm going to grab the bounds to the face, and I'm only going to process that using OpenCV. Then the getImageComposite function will return the processed part of it and composite it back into the original image just over the face, right? So if I go in here to my DSP utils, my .m function, what I can actually see here is inside of process image is a giant switch statement, right? And it's case 1, case 2, all the way up to case 11. And there's a couple of things that I can do here. So as I switch between the processing types that I'm going to be using, I'm going to be going from converting color, right? So taking a bitwise not, to if I'm in case 2, I'm actually going to convert over to BGR format, and then I'm going to do exactly that code that we had before where I'm going to be setting the values. So the first value that I'm going to set, the blue channel all the way to 255, the red channel all the way to 255, and just to make a point here, I'm also going to be setting The next pixel, only the blue channel to 255. So essentially, I'm going to set the next pixel equal to blue, just to be sure that you know that this is an array of pixels that you can access. So I'm actually going to be doing this for I and J right here, and I'll be going to a counter pixel. All right, so as I and J are less than counter, I'm going to be setting things equal to this. Every time I come through this process image loop, I'm going to increment counter. So I'm actually, until I get to, once I'm above 50 pixels, I set it back to 0. So essentially what this is going to do is it's going to fill in the pixels that I have with a solid value, a 50 by 50 square at maximum, but it's going to be counting. So it'll take a small square and then a big square, small square, and it'll grow to a big square. Right? The other image that I want to talk about here is the convert color, where I'm actually just taking the average of my image copy here, so my average pixel intensity for the blue, green, and red. And then I'm actually going to use the put text method, which you can go in here and look and see how exactly it works, but essentially I'm going to be placing text inside of the image, and that text is going to be, I'm just going to be taking up the pixels that are inside the image so I can display the blue, the green, and the red value. And again, it's only going to be over the face, right? So without further ado, let's look at cases 1, 2, and 3. And the way that we are going to go from case 1 to case 2 to case 3 is if I go over here to my storyboard, I've actually set up, so I'm going to display the stage that we're in, but I've actually set up a couple of swipe gestures. So whenever I swipe left, that will decrement the processing stage that we're on. Whenever I swipe right, I'm actually going to increase the processing stage. So it just kind of moves us where we are inside of that case statement. Okay, so let's go ahead and start, and we'll see what this looks like going from stage 1 to stage 2 to stage 3. Right? And again, I'm only processing the face and compositing it back into the image. Okay. Okay. So now I can see I'm doing no processing right now, but the second that I actually swipe, I'm doing an inversion on top of only the face, and you see that it's bounded by the face as I get in here, right? So bounded to the face. Right? Now, the second that I do another swipe right, we're actually setting the pixels to that block where it gets bigger and bigger. Every time it goes through, we get a bigger and bigger image, bigger and bigger pixel setting. And if you really were to zoom in on that, you'd notice that there's a slight blue line right outside the pink where we're actually going to the very next pixel. This is on a retina screen, so it's really tough to see. Right? And now we can actually go through and look at the statistics of the image. So if I zoom in on my face just a little bit here, I can see the average blue, green, and red values. And again, that's put text. So if I go too far out, I can actually I can start to get the text to actually just disappear because I'm only taking my original image and compositing it back into the original. And you can see that it does have just a little, you'll see some lines on it. It sometimes has a little bit of trouble compositing the image all the way back in. And that's because I had to do some rotations on the image. And so sometimes we lose a line of pixels when we do the processing. Okay, all right. So now I can go back to the inversion. Now let's look at some more examples in OpenCV. Okay, so let's go beyond some of the basic operations that are part of OpenCV. Let's talk a little bit more about color conversion as we talked about. So to display properly, we need to use BGRA as the initial format, right? And so what we might want to do here is convert color from our input image into a copy, BGRA to BGR. And that guarantees that most of the filters, most of the processing that work on BGR or RGB images are going to work for our color conversion. We really just need to get rid of the alpha channel. And then whenever we're done processing this image, we can transfer it back into our image using BGR to BGRA or gray to BGRA, whatever it is that we've converted, right? So if we convert it over to grayscale, we can convert it back into BGRA format, and that guarantees that we'll have a UI image, a core image that we can display properly, right? Now, There are also other color conversions that we can do that don't just get rid of the alpha channel, but actually make color representation much more intuitive. And the first one that we're going to look at is converting from RGB, where let's say we have R, G, and B here. They all go from 0 to 255, and depending on the mix of B, G, and R that we have, it kind of gives us these different colors. As a mix of all of them equal to 255, we get white. We'd like to convert that over to something that's a little more intuitive, something that's maybe separated by hue, saturation, and value, right? So we actually talk about things on a color wheel rather than this representation, right? And this will be easier, more intuitive for us to represent color with, and we'll see why in just a second. So let's say we have an original image like this. Now, this original image, remember, is represented in OpenCV as 3 matrices, B, G, and R, right? And we can also convert it to grayscale, which we get rid of all of the channels, and we just have one matrix of the grayscale values. But let's say we can actually take, instead of just looking at all the colors combined like we're used to, let's take each of those colors, each of the channels that we have, the B, G, and R, and represent them as if they were grayscale images, right? We're just going to break apart the image and look at each of them like a grayscale image. And what we can see here is we have a red channel, a green channel, and a blue channel. And what this tells us is that in the red channel here, we actually have, clearly the nose has a lot of red inside of it. We can see that from here, right? So these are very large values in the red channel. The green channel, actually, there's green in all of this image. And actually, green is very, very sensitive. It's part of the human eye that's most sensitive to all different colors. So it's sensitive to reds and greens and blues, lots of different things. And so that's why this G image here actually looks more like a grayscale image than any of these other images. And then we can see the B channel, the blues, clearly there is a large blue channel that's part of here. There's not a lot of blue in the nose, even though there actually is, a decent amount of green that's in the nose, right? Now, really, we'd like to represent this better, right? These channels don't tell me what color it is, because I don't think of terms of color as red, green, and blue. I think of, combinations of red, greens, and blue. I think of them in combinations of everyday colors that I'd like to see, like I name things pink, orange, or purple, shades of blue, light blue, those types of things. And so the color space, hue, saturation, and value is very related to how we perceive color. And instead of breaking things apart into R, G, and B, we're going to break things apart in terms of the color, which will be the hue plane. So it'll be one channel that represents color. There'll be a saturation plane, which represents how intense, how rich is that color, and a value plane, which is, okay, well, how dark or bright is it as part of that image? Now, when we take the same original image that we had and break it into the hue, saturation, and value components, well, here's what we get. In terms of value, right here, the value that we actually get is it's very bright on the nose and the eyes, right? And we can see that it's very bright on the nose and the eyes right here, very, very bright. The saturation plane, we see very rich colors, right around the center, very rich blues, rich reds, right here. And the hue plane actually starts here. So the red plane is actually 0. So all of the things that are close to being red, you see is very dark. This is a red color, right? And if we look and we keep going around this, well, the blue plane is actually much larger values. So these will actually be larger grayscale pieces that we have right here where we see the blues, right? And so now one single channel represents color. And it's much more intuitive to look at color as something between 0 and 255 rather than a combination of 3 different colors, right? So that's color conversion. And we'll take a look at an example of that in just a moment. But first, we also need to talk about edge detection, because this is another complex operation that we're going to talk about in the demo in just a second. So we can actually use linear filters to get something called the gradient of the image. And the gradient of the image is really just the derivative, right? So if we were to say, okay, I'm going to take 1 pixel, right? So let's say I've got something that's going from 0 to 2,000 pixels, right? So it's an image that's 2,000 wide. I'm going to take 1 row out of the image and just plot it, right? Like you would just a normal graph. What I can see here is there's an edge right at about 1,000, a very strong edge where we go from low pixel values to high pixel values. Now, the problem with taking the gradient right here, just taking a difference along this of these filtering, is that all of this noise that I see down here, that also has a very high derivative. So if I look at just the raw derivative of that, the edge itself gets completely washed away inside of that. So we need a better solution than just taking the derivative of the raw pixels, the raw row. And the way that we do that is through smoothing, right? So in addition to taking the derivative right here, we're going to do a smoothing first. So we do a smoothing operation here using a Gaussian kernel, and then this pixel that we have, this 1 pixel row, we're smooth out the edge a little bit, but we get rid of a lot of the noise that was in there. And so now when I take the gradient of this, when I take the derivative of this smoothed curve, I can actually very easily see, oh, yeah, there's an edge right there. I have a really nice response, right? And that's the image gradient that I have right there. And so we're going to do a smoothing operation and then a gradient operation. We can also look at things like curvature, right? Where instead of using the differentiation, we could actually use a kernel that looks like this, right? And so that means that anytime we have a line, we will actually get a response from this kernel, right? So we smooth it, and then we run this across it, and anytime there's actually a dip, right? So down, constant, and then back up. That's a line. We have two edges right next to one another. This would be a line detector that we have right here, just by running that in the image, right? So if I were to run those examples, do a smoothing operator, and I take it on this image, we can immediately see some of these are the vertical edges that I'm actually highlighting inside of this image. We can actually see that, yeah, this is a really good gradient. We can see the lines that are right here. But can we do better than this, right? Can we do better than just taking the derivative? Can we actually know where a line is, where an edge is in the image? And we can. And the way that we can do that is checking for local maxima that we have inside of this derivative image. Because where we have any local maxima, well, that right there is probably a line. And we can actually check to make sure it's a line and then go along that line in the direction. And the way that we do this, the most common way of doing edge detection, something that works very well, is something called canny edge detection. And canny edge detection is a 5-step process. Just going to give you a high-level overview. But essentially, we do the smoothing and the gradient, which we've already talked about, steps 2 and 3. Then we have, okay, let's find all of the local maxima. Where is the gradient greater than some threshold, right? And it's got to be greater than some threshold that's kind of large. Then we're going to say, okay, wherever it was large, let me look at the line. And let me look along that line, and let me go left and right, or, at an angle, wherever that line is, wherever it's oriented. And let me apply a lower threshold and say, I'm going to take anything that's above this magnitude, but also in line and connected to the local maxima that I've already found, I'm going to call an edge, right? So let me give you an example of what that looks like. Right? So we're going to see if things are above a first threshold, and then if it's above that first threshold, we're going to extend using a lower threshold to see if we have edges. So let's say we have our gradient image. We're in step 3 right here. Let's say we find some local maxima, and we see that, oh yeah, this right here, there's a couple of points here that are above our first threshold. What we'll do is we'll define perpendicularly, we'll look left and right, and we'll say, okay, we're going to lower our threshold. We're going to say, okay, let's do a smaller threshold, and I'm going to look along this line, and I'll go ahead and extend out. I'll say, yeah, anything that's at this lower threshold, but on this line right here, is part of the edges that we have. And if I do that, I get a very, very strong edge along here. Actually, we get a very good edge representation using canny edge detection. However, we have to set all of the thresholds that we have as part of canny edge detection. So if we want to do this using OpenCV code, it's actually very simple. There's a canny edge detector function that I give it where we give it the input and the destination, right? This is where it will save all the edges. Then we have to give it the 2 thresholds that we want, and we also have to give it the size of the gradient that we want to use. So this is the size of the gradient. How big is the gradient and the smoothing filter that we want? the large and the small threshold, and it will save that inside of the output right here, and we can immediately display our canny edge detection. Okay, so we have edges. Maybe what we want to do with those edges is just a little something more. So let's say that what we have here, this is returned. This is an image that's returned from our canny edge detector, and it has a value of 1 where there was an edge, and a value of 0 where it didn't see an edge, right? And so let's say it came back with this. Well, one of the first things that we can do is say, okay, well, each of these edges, they might represent objects inside of this image. And so what I'm going to do is all of the edges that are there, I'm going to say if they are touching one another, if the pixels are touching on the corners or on the sides, anywhere it is, I'm going to say that's one connected component. So I'm going to go through this whole thing and I'm saying, oh, this is a connected component search. So all of these are connected to one another. All of these are connected to one another. And hey, there's a big square over here that's connected to one another, right? So one of the things I can do now is say, okay, well, I'm going to detect the contours, the outside of each of these components that I have right here. And that's as simple as going around and say, well, this is a contour of some object that I found in the image, right? And that might be important for tracking applications, for just looking at a blob as it moves around. There's lots of different applications for contour detection. So we're going to look at canny edge detection and doing contours in Xcode. So let's start it out. Let's see what we can do. So the first thing that we'll do here is we're going to look at case 4, which is looking at that hue, saturation, and value planes. Right? So what I've done right here is I've converted from BGRA to BGR, and then I'm converting from BGR to HSV. And the reason I do that is because there is no BGRA to HSV, right? So I have to convert it over to BGR and then BGR to HSV. Now what I'm actually going to do is I'm going to split each of those layers, right? And what I'm going to do here is I'm going to add into one of the layers, I'm going to add it into the hue, a value of 80. So what I'm actually doing here is changing the color, the natural color that's in the image, I'm changing it, right? So I'm doing a shift in the actual color that's here. And then I will merge those layers back together. So I split the layers out, add 80, merge them back together so that they're one matrix. And now I can convert color. I can go HSV to BGR, and then BGR to BGRA. Right, so all of this was just a long-winded way of adding something to the hue channel and then converting back. Right, so let's really quickly see what that looks like before we move on to canny edge detection. So we'll run this and build it. So we'll see what this adding to the hue component 80 is right here. Now, first notice that I'm wearing something of a blue shirt right here. So we'll actually see what this looks like when we convert and add what we change the hue of my blue shirt into. Okay, so there's stage 1, 2, 3. Now the next stage, now we've actually done a hue conversion. And I can actually see if I can get the value of this. We've actually converted the blue to more like a yellow or a greenish color, right? And if I actually come in here and I were to say, oh, well, I have a red right here. If I actually take this red color over, we can immediately see it converts it over to a green color, right? So red was at the very low end of the spectrum, right? So I'm able to convert those over using my HSV. Now, let's actually look back here to what happens when we look at our canny edge detection. Now, we've already defined what this code does before, so let's just look at what the output looks like. So I convert it over to grayscale, perform canny edge detection, and then display the result of the canny edge detected image. Right? So we convert over. Well, this is a thresholding, a blurring, right? So this is a Gaussian blurring, so I'm in case 6. But let's go up here to case 7, and here's my canny edge detector, right? It's only detecting edges that happen on my face, and it's actually doing a fairly good job. It's getting a little bit caught up in some of the different places that are along my face, but essentially it's still doing a pretty nice job performing that edge detection, right? Now, we also talked about contour detection. And contour detection, we built it on top of the OpenCV implementation, right? So, sorry, the OpenCV canny edge detector. So what we can actually do is first do a canny edge detection, and then I can call the function find contours. And so it connects all the connected components together, and then it takes those connected components, and it draws a contour around each of them. And what I can do is say, hey, for every single contour that you found, draw a bounding box around those separate contours. So these are the separate parts of the image from my canny edge detector. And if I run this, boom, I can actually see that there are all of these contours. You know, it notices my eyebrows are fairly consistent, my eyes are fairly consistent, nostrils, most of the strong edges that we see inside of this image are detected in the bounding box that's there. But we don't just have to display a bounding rectangle around all of those separate images. We can actually also do the exact same thing that we did before, but we can just draw those contours straight onto the image. So if I do that, here's what it looks like when I draw the contours straight onto the image, right? So each color represents a different part of the image, a different contour, right? Okay, so after this, let's talk about how we can use the hough gradient, the hough circles, and how we can actually do a little bit of tracking using Haar cascades. Okay, so let's move on. Now that we have kind of a grasp on edge detection and looking for connected components and contours, let's do even more with the computer vision aspect of this, and let's actually look for specific shapes. Now, the way that we typically look for shapes is through an algorithm that was created and is typically known as a hough transform. Right? So a hough transform can be used for lines, triangles, squares, circles, generic edges, these types of things, but it's essentially looking for a specific shape. And in general, a hough transform consists of doing edge detection, and then for each detected edge that we have, every point that we have that's on a detected edge, we draw some type of shape. It's the shape that we're looking for. And every time we draw a new shape, we add to the shape. So in this example, we do edge detection on these coins that we have right here. And then every time we have an edge, we draw a circle. And so whenever we draw a circle along that edge, we're accumulating, we're adding every single point along this edge. We draw a circle and add it, draw a circle and add it. We're actually, wherever we find a circle of the same radius that we're drawing, we're going to keep adding up right in the middle. And we can see these little white spots are where local maxima are occurring, right? And we'll do that for a bunch of different circles at a lot of different points with a lot of different radiuses. And then inside of that X, Y, and radius space, we'll just look for those local maxima. And we'll be able to tell where the circles are in the image. So if we want to look at hough circles in OpenCV, we just simply need a vector right here, and we send in the image that we have. We send in something where it can save the circles. We tell it that we're doing a hough gradient right here. And then we tell it, hey, what's the maximum distance between the centers of the circles that we find? What are some of the canny edge detector thresholds that we're going to use for converting over? And what's the magnitude of the local maxima that we need to have? What's the minimum magnitude we should have in order to say, oh yeah, this white point right here, that's a circle, right? So for this will be 40, but that'll be something that we'll have to play with in different lighting conditions, right? So that right there is the hough transform. We can also do different classifications based on Haar cascades. Now, we had talked about Haar cascades before in the advent of finding faces. But really, because this is an open source toolkit, we can define and look at defined Haar cascades that have actually been used and trained for all sorts of different types of things that we might want to track in an image. So if we go look online, some of the things we can find a lot of pre-trained cascade, Haar cascade classifiers that we just need to load up into OpenCV. And so here's a link for quite a few things. These are actually stored as XML files, right? So they do have face detectors. We're not going to use them because we're using core image for face detection. But as part of the face, we could actually look for specific parts of the face using Haar cascades if we wanted to. It's a very fast implementation. Or if we wanted to, we could create our own database and train our own Haar cascades, save it as an XML, and be able to use it later. This is not a trivial operation because we need a huge database of positive examples and negative examples, right? So here's what it does look like, here's what it doesn't look like, and we have to train up our Haar cascade classifier. However, we're still going to just concentrate on using the API. For iOS, if we want to use a CV Haar cascade classifier, we can simply load it up, right? So here I'm assuming that there's some file named Haar cascade underscore frontal face underscore alt2 .xml, and I actually just get the path to it right here. And I can use that to load up a Haar cascade classifier. So I have a CV cascade classifier right here. This is the variable classifier, my object. That is equal to a CV Haar classifier, and I just point it to where that XML file is located, and it will load up everything that I need for this CV Haar cascade classifier. So now I've loaded it up. I only need to do it once. It's saved. Now I can use that to run that Haar cascade classifier on an image and say, hey, where are the different points of tracking that this Haar cascade has been trained to classify. So if I want to run my classifier, let's say a grayscale image, I can actually just call the classifier .detect multiscale. So detect this at different scales of the image, right? And I'll give it the grayscale image, and I'll give it something to save the objects that it finds in. It's just a vector of rectangles. And then I can actually iterate through all of those rectangles and just draw a rectangle on the image right around wherever I detect whatever it is that that Haar cascade has been trained to classify, has been trained to detect, right? And so using this framework, it's very easy to go find an XML file and load it up and be able to use it, actually detect anything that I want, anything that has been trained, right? So we'll give an example, a demo in just a moment, but use OpenCV, go out and look at a lot of the examples that are out there. There's so much that you can do with OpenCV. We've barely scratched the surface, but I'm giving you a lot of example code to get you started, right? So every algorithm, it's written by a whole open source community. That also means that each algorithm may have slightly different semantics, slightly different ways that you use the code because it's not unified. That's okay. It's an open source community. It has the advantage of being very comprehensive. It's absolutely an industry standard. People use it all the time. So go in, have fun with it. You can get this example from GitHub. Next time when you actually come to class, come ready to perform some computer vision. Use this as the base plate code, and we're actually going to update it and do some different things. So let's do our final demo where we actually load up a pre-trained Haar cascade classifier. We'll also look at the hough transform. Specifically for our Haar cascade, we're going to look at classifying and finding the nose in the image, which is something that core image doesn't do, so might as well use that. Okay, let's do it. Okay, so if I come over here, I can see what it looks like to use my hough circles code. We'll go ahead and run this on the phone here. But essentially, what I'm going to do, we'll convert to grayscale. We'll do a little bit of blurring to get rid of some of the noise. And then I'm just going to run, hey, find all of the circles that are inside of this image with a magnitude in the parameter space of about 50. Okay? Okay. And then for each of the circles that I've found, the circles.size right here, it's a vector. I'm just going to draw the center of the circle, and I'm going to draw an outline of the circle that I have right here. So let's go ahead and load this thing up. We'll go across all the different types, things that we've done in the past here. Canny edge detection, contours. Okay, now here is my hough circles. Now you'll notice I don't really have, it's not really detecting anything. So, well, maybe we actually need to adjust the magnitude of the local maximum. We'll change it to 40 and rerun. And there we can actually see it's actually finding circles right around my mouth now. Ha! Ha! It's like a surprise detector, right? So that is our hough circles detector. Okay, great. So now let's go to this last little thing, a generic Haar cascade, where I've actually loaded up. I have a convenience function inside of here that is for loading a Haar cascade with a file name. You just give it the file name. Right here we have this nose.xml that I've loaded up. And so you can actually, in the view controller, the Haar cascade is loaded right here, self.bridge, load classifier with file name nose, and it will load up nose.xml. And then inside of the bridge function, it actually uses that to detect multi-scale, save the objects, and then draw, hopefully, we'll draw something around my nose right here. So, pretty good. It also seems to think that my mouth is a nose for whatever reason. So if I do a little distortion or something, it has more trouble with it. But still pretty good. Can find my nose. Look at that. Amazing. So yeah, go for it. Have fun. Look at a lot of the different things that are involved in OpenCV. You can do a lot with this framework, and I've given you a lot of starter code to be able to look at this pretty well. So yeah, please go have fun, and let me know what you think.